Welcome to The Explainer. We hear about machine learning all the time, but have you ever wondered what's really going on under the hood? Well, today we're going to crack open the engine and look at one single statistical idea that, believe it or not, secretly powers some of the most common AI you interact with every single day. So let's start with something we're all familiar with. We've all seen a computer draw a line through a bunch of data points, but how does it pick that specific line? There are infinite possibilities. It's not just about getting close. Nope, there's a much more elegant and powerful principle at play here, a secret engine that makes the decision. All right, so here's the game plan. First, we're going to meet this secret engine. Then we'll see how it's been hiding in a model we all think we know. After that, we'll throw a totally new kind of problem at it, find a new solution, and in the end, we'll uncover this really big, universal idea that's fundamental to AI.
So what is this secret engine that's driving all this learning? It's a concept from statistics that's actually beautiful in its simplicity. It's called likelihood. The best way to think about likelihood is as a plausibility score. Let's say you've got some data. Likelihood lets you test out any explanation, any model you can dream up, and it gives you a score that tells you just how well your model explains the data you're actually looking at.
Let's make this real. Imagine these dots are a bunch of house prices we've collected. Now, to try and understand them, we could make an assumption. We could say, you know what, maybe these prices all come from a bell curve, or what's officially called a normal distribution. The only problem is there are infinite possible bell curves. So which one is it?
We could test a short, wide one, or a tall, skinny one. We could shift it left, shift it right. For every single curve we try, the likelihood score tells us which one is the most plausible origin for our data. So our goal becomes pretty clear. Find the one single curve that gives us the highest possible score. And that process, it's called maximizing the likelihood. Okay, now this is where things get really cool. This idea of maximizing likelihood, it has a secret connection to something most of us probably did in a high school math class: fitting a line to data points, also known as linear regression. And here it is, the big aha moment. That method we all learned, finding the line that makes the squared distances to all the points as small as possible, that's not just some random rule somebody made up. It turns out it's the direct result of making one assumption, that the errors in our predictions follow that same bell curve we just talked about. When you maximize the likelihood of your data with that assumption, the math simplifies to the exact same process as minimizing the sum of squared errors. It's incredible. So, right there, maximizing likelihood is the true why behind one of the most fundamental tools in machine learning. It just goes to show you there's usually a much deeper reason for why we do things the way we do. All right, so now that we have this powerful engine, let's take it for a spin on a totally different kind of challenge. Okay, so we've got this maximum likelihood principle down. So let's see if we can use it on a completely different problem: classification. This isn't about predicting a price anymore. Now we want to predict a category, a simple yes or no. For example, is a patient diabetic or not? At first glance, you might think a straight line could still work, right? We could just fit a line and say, hey, anything above the line is Class A, anything below is Class B. And for really clean, perfectly separated data, yeah, it might even look like it's doing a decent job. But here is the fatal flaw. Linear regression is absolutely obsessed with minimizing that squared distance to every point, which means it is ridiculously sensitive to outliers. Just look at this. We add one far-out data point, and it yanks the entire line way off course. It completely destroys our decision boundary, and suddenly the model is getting things wrong that it used to get right. It's a clumsy tool for this job. Clearly, we need a better tool, something that's actually designed for this kind of yes-no question. And this is where our next model, logistic regression, steps onto the stage. The absolute genius of logistic regression is that it doesn't even try to fit a straight line that shoots off to infinity. Instead, it fits this beautiful, elegant S-shaped curve. And this S-curve has a very special property that makes it absolutely perfect for our problem.
See, a linear model can spit out any number, negative a billion, positive a billion, whatever. But this S-curve, its output is always squeezed between 0 and 1, always. And that simple constraint is a total game changer. Because the output is always between 0 and 1, we can now think of it as a probability. So if the model spits out 0.9 for a patient's data, we can literally read that as the model is 90% confident this patient has diabetes. How useful is that? It's an incredibly intuitive way to understand what the model is thinking. So we have this amazing new S-curve.
But just like with the straight line, there are still infinite possible S-curves we could draw. So how in the world do we find the single best one? Well, by now, I bet you can guess. We're going to go back to the exact same core principle we started with. We fire up our secret engine one more time. We maximize the likelihood of our data. Now, the math is a little different this time, sure, but the fundamental goal is precisely the same. Find the settings for our S-curve that make the data we actually collected the most plausible, the most likely outcome.
But there's a catch. This method can sometimes be, well, too powerful. A model, if you let it, can learn to draw an absolutely wild, squiggly line that perfectly separates every single dot in your training data, even the noisy, random ones.
This is a classic problem called overfitting. The model hasn't learned the general pattern, it has basically just memorized the training examples. The solution is a clever technique called regularization. Think of it like adding a penalty for being too complex. It encourages the model to find a simpler, smoother, more general boundary, which almost always helps it perform better on new data it's never seen before.
Okay, we have covered a ton of ground here, from simple lines to these elegant S-curves. So let's zoom out and pull this all together for the final and most important takeaway. We started with what seemed like a simple question. How do we find the best line? That question led us to this deep statistical principle. And then that very same principle, maximizing likelihood, gave us the blueprint for a completely different kind of model, built for an entirely different task. It's the common thread, the shared DNA that connects these foundational tools of AI. And that really makes you wonder, doesn't it? If this one core idea is the engine behind both predicting numbers and classifying outcomes, where else is it hiding in plain sight, secretly running the incredibly complex AI systems that are all around us? Thanks for joining this explainer.